Tom's just launched ROSReality. If you listen now, you'll hear it confirm that it's established a connection with the ROS server.
Connected to ROS server.
Next, Tom's going to find the orange Vuforia tag. This allows us to track the robot into Unity's coordinate system, so we can transform sensor data to later visualize it. The turtlebot is now tracked in Unity's coordinate system. The grey card shows where the robot thinks it is, and the blue arrow shows the direction the robot thinks it's facing. The buttons you can see here follow the robot at all times, so they're easily accessible. We've now switched on the LiDAR visualization. This is a helpful debugging tool as it allows developers to understand which obstacles the robot is able to perceive using its LiDAR. This is the secondary menu. We'll now demonstrate the D-pad control system. This allows the user to teleop the robot, which is helpful when debugging as it helps the user test the robot's SLAM process is tracking the robot correctly. It also demonstrates that the ROSReality library has the ability to publish arbitrary commands to any ROS node. It can be extended to send any communication, including, for example, navigation goals, as we'll demonstrate later. ROSReality commands can also be triggered by the user's voice. Listen now to hear us tell the system to start while following and then stop. The library supports publishing any command by voice if configured. Run while follow. While it's while following, you'll notice the robot's perceived location shift relative to the real robot. This shows the user that the SLAM system is losing track of the robot, which is a very helpful tool for understanding difficulties in the robot's navigation system. Stop movement. We'll now send a go home nav goal to the turtlebot. While we were developing ROSReality, we noticed that the robot's perceived location would correct itself when the robot went around corners, reducing the amount of drift. We think this is because when the robot rotates, SLAM can measure landmarks from multiple angles to accurately orient itself. This is just one example of how bringing sensor data to augmented reality can speed up the development process.
Beacon detected.
ROSReality also supports adding arbitrary objects to the scene. Here we detect a yellow-colored beacon, which was published to a random location. The library is designed to be extended to support tracking other arbitrary objects perceived by the robot. Finally, the user can send navigation goals to the robot, as we'll demonstrate now. Unfortunately, our path visualization worked in the simulator, but it could not be localized correctly on the device. A future extension could involve getting the path working, to assist developers with debugging the robot's planned route. Hopefully this demonstration has highlighted the extensibility of our ROSReality library. We have adapted it to work on the robot rescue task from assignment 1, but it is designed to work with any robot. Thank you.